Yeah, yes,
Yes, yes,
please.
please do. Yeah. Let's go live. Okay, so welcome everyone. I am Bhas Bapat. I am the coordinator of rather the chair of the committee that is coordinating the formation of the Department of Science Education at IISER Pune. We have begun this month, or a little over a month now, a series of talks on science education, which we call Introduction to Science Education series. We have had quite a few talks on diverse topics in the last month and a half. And today's talk is the last of the talk in the first series. Uh, we are we are very close to the end of the semester now. The semester ends at the end of this week. We'll have exams. And we will certainly come back in the next semester with another series of talks, perhaps on a new set of topics. But this first series, which was essentially an introductory series, talked about a variety of things, curricula, about how students learn, what is important in the textbook, and stuff like that. Many of the talks in the series earlier were focused on science-related topics. Today we have a talk which is focused on mathematics education. Our speaker is Professor K. Subramaniam from the Homi Bhabha Centre for Science Education. He is better known as Ravi, and Ravi has been the director of HBCSE for quite some time. He stepped down only recently, and he's now back to being a regular faculty member at HBCSE, focusing more on his research than on administration. Ravi's interests are primarily in mathematics education, but he didn't begin his career in mathematics. He started with a BTech in aeronautical engineering from IIT Madras, after which he switched gears after a gap to do MA in philosophy, followed by a PhD in philosophy from IIT Bombay. He then took up mathematics education as his primary research interest, and then came to the Homi Bhabha Centre for Science Education. Ravi's main research interest is mathematics education at the school level, and he has worked on development of curricular and co-curricular materials, and also in teacher training. And his research focuses on the cognitive aspects of mathematics learning. He has developed quite a few curricular resources, written many books on mathematics education, and he's currently working on a very interesting project, which has to do with the importance of mathematics education, or numeracy, perhaps might be the word for it, and its role on social change and generally for social benefits, in particular health related matters, if I understand it right. So we have today a speaker who comes with a very diverse set of experiences, and today's talk is also different from the rest of the talks in the series in that it focuses more on mathematics education. He's going to talk to us today about why students find the transition from uh, arithmetic to algebra hard, and I'm sure this is something that will find consonance or resonance with many people here. Many people experience this difficulty either themselves or see children around them facing these difficulties. And we look forward to Ravi shedding some light on why this difficulty is the way it is. Over to you, Ravi. We typically have a talk for about 45 minutes. Questions can either be interspersed or at the end, the way you prefer. There might also be some questions on the YouTube live stream, and I'll collate them and ask further questions to you later at the end of the talk. Right. So over to you, Ravi. You can share your screen if you wish to, and
thank you.
You can pause me for anything if you need.
Sure. Thank you, and thank you for inviting me to give this talk. Bas and the rest of the team managing the science education program. It's a great pleasure and honor to be here. I would prefer to be present physically in IISER Pune. That is not to be this time. Perhaps on another occasion, I'll be there, and I really look forward to that as well. Before I begin my talk, let me reiterate that please feel free to ask questions, interrupt me in the middle of whatever I'm saying right from the beginning. In fact, I will also ask you some questions and you can respond in the chat. I'm not very sure if I will be able to see the chat. So, Bas, could you?
Sure. I'll anchor it here.
Yeah, just unmute your, speak up, and the same goes for everyone else. So if you feel comfortable, you can speak up and ask me a question or make a comment or whatever. So let me begin by sharing a few slides. Okay. So I think that's visible, the slides.
Yes, they are.
So that's the title. Let me just move these windows a bit. So why do students find the arithmetic algebra transition difficult? So that's a sort of overview of what I'm going to say. Some introductory remarks going from arithmetic to algebra. Then how does algebra appear through the student's eyes? Then I talk a little bit about something called the conjoining error. I'll explain that. And then that leads on to something that I call algebraic principle. And so we'll discuss that. Then, of course, I'll talk a little bit about why the algebraic principle appears, why it's needed. And that sort of highlights the difference between arithmetic and algebraic ways of solving problems. I'll illustrate that with an example. And then I'll just briefly touch on how this could be applied to teaching. Teaching not quite algebra, but arithmetic as a sort of preparation for algebra. And this is drawn from work that we did. Of course, it's work done, whose work was published about 10 years ago. So it's not new work, but I've been reflecting on this, and so perhaps some things might be new. Of course, for those of you who have heard me before on algebra education, there won't be anything really new in this talk, and so my apologies about that. So perspectives and some comments keep changing, but the main message and the code remains the same. Okay. So now, of course, algebra is the language or the tool to express generalities, to prove in mathematics, and to construct higher order concepts or higher order objects and so on. So it's really a kind of gateway to a lot of mathematics and a lot of the applications of mathematics. I'm not going to dwell on this in detail, but I think many of you will agree and you will appreciate that that's the case. And so it's very important for students to learn some algebra from the point of view of open to them for higher learning in the sciences and social sciences. In fact, wherever there's a significant application of mathematics, engineering, and so on, you will need to master algebra. So if algebra remains a sort of gray or a black box, something also probably producing anxiety, then it's definitely a hurdle. And so one needs to address this issue. Algebra is also acknowledged to be difficult, and there's some evidence for this which one can see from various tests and so on. So today I'm not going to go into those sorts of evidence, but there are two kinds of tests from across the world and also in India. One is what are called achievement tests. Now these are typically conducted by, say, the NCERT conducts them at somewhat regular intervals, though it's not been very consistent. The ASER or ACER from Pratham also conducts these tests. They are pretty regular, but then they do a very rudimentary version of achievement test in mathematics. The NCRT test is a little more elaborate and sort of across different grades, they have different tests. But in contrast to these, there are what are called diagnostic tests, which specifically identify student hurdles, and there are quite a few of them. There used to be diagnostic tests conducted by educational initiatives for many years. That's one that's available. But I think now they don't have too many publicly available reports. But so, in any case, in the Indian context, such tests are very few, and a lot more work needs to be done. But if you look internationally, of course, there are many tests, and there are also tests conducted as part of research studies, which are similar to diagnostic tests, and they go somewhat in detail. So from all of these, we know that students have difficulty with algebra, and we have a fair understanding of what these difficulties are. That's what I'm going to talk about. Now, you might say that going from arithmetic to algebra, of course, algebra is difficult, but what about things like fractions and what about negative numbers? Are they not the difficult topics? Are they not really the hurdles actually for algebra? Now, there is a lot of truth in that statement, or that question is very valid. In fact, fractions and negative numbers are a sort of preparation for algebra. That's the main reason why they are there in the curriculum. Fractions, as opposed to say decimals, which have a wide application, but not. So they're primarily because they aid in proportional thinking and reasoning, and because they are a preparation for algebra. And similarly, negative numbers. So it's quite valid to say that look, the difficulties with algebra actually stem from difficulties with fractions and negative numbers. That's what really causes them. Now, however, there is something about algebra and the algebraic principle which actually extends to fractions and negative numbers. That's something very interesting. And what I am saying is that the difficulty with algebra is not very different from the difficulty that students have with fractions and with negative numbers. You could say vaguely that all of these are abstract; they don't correspond, like whole numbers, to something out there in the real world very clearly. Now, that's one part of it. But there's something, in fact, all of them are related to what I call the algebraic principle, and we'll come to it. That's something quite interesting. Okay. That's the question I was just asking now. Are they the main motivators? Okay, so let's move on to how algebra looks through the student's eyes. And here I'd like you to think about this and respond. So, what's the most noticeable thing about algebra to a student who has just encountered? What do you think is the most salient things that thing that strikes the most? Let me see if I can see the chat. Oh yeah, I can see the chat window also. So
Request people to respond either in the chat box or I can unmute you if you want.
Okay, so
So one of the answers.
Joyce says alphabet. Yeah, thank you. Anyone else? Numbers. Okay. I'm assuming that students have done arithmetic and then they're encountering algebra. So numbers would be familiar. Of course, what Shakama probably means is a mixture of alphabets and numbers. Yes, that's true. Yeah. So let me move on. And so quite true that students see letters and also they see letters along with numbers. And someone has said variables, Vas says arithmetic operations on letters. Okay, letters are getting multiplied and divided. Something not known. Okay, so lots of interesting responses, but yes, I think the most salient thing is letters and the fact that something is being done with letters along with numbers, and maybe the letters stand for something which we don't know what that is. Okay, okay now, okay, I skipped that question, so let me go back. Oops. So how might students interpret these letters? Because I think the way we use letters outside of algebra is that letters typically stand for objects. Maybe for names like initials or some specific objects, some qualities. They may even stand for a word and so on. So here is an example. In fact, that's from an algebra class, which says that you can't add 3a and 2b because you can't add apples to bananas. And so the whoever's saying this comment, maybe it's a teacher or maybe it's a student, sort of is implying that A is standing for apples and B is standing for bananas. And so here actually A and B uh, apparently stand for objects. And this is quite a natural interpretation for a student who comes to encounter letters for the first time. And this is something that we should really be careful about because in algebra, letters don't stand for objects. And here is another example from the literature, one of the errors which is talked about. So there are 6 white and 3 black cars outside. Write an expression for how many cars are there. Any guesses what it might be? How students might respond to this? Okay, I keep asking this because one of the things that teachers need to do, and there are actually many teachers are good at this, is to anticipate what students might think, what the students' responses might be. And so there is Bas. It's clear that he's a teacher, experienced teacher who anticipates. So that's really what many students write. And 6W plus 3B. Now that's sort of reasonable, but it's not algebra. Because in algebra, letters stand for numbers and they don't stand for qualities or objects or something. Now, of course, you might say, oh, I should figure out how to do that. You might say that it's not the case that in the whole of algebra, letters stand for numbers. Letters can, of course, stand for other things. In fact, we can use symbols which stand for a multitude of various kinds of things. But in school algebra, it's important, I think, to emphasize that letters stand for numbers, maybe different kinds of numbers. And that's a very important thing because it's important. It's a provisional view. It may not be only standing for numbers. It can stand for other things later on, and that becomes important. But it's important for students to pull away from other habits and to see that when we write many things down in school algebra, actually letters are standing in place for standing for numbers. And this is a very important perspective that students need to have. Now, and this is now in many formulas that we use in mathematics, simple interest, perimeter of a rectangle, and so on. You may say that length, L is the length, B is the breadth, or P is the principal, and so on. Now, these are not qualities or objects, but actually they are numbers. In the sense, it's the length, which is the measure of the length, and they stand for numbers. So this is an important difference which one should pay attention. Okay. So okay. So here is something that we tried with the students, and something called the letter number line. It's a very useful device actually in teaching algebra. So this is a number line, and there is a window which is shown by the rectangle, and it's looking at some part of the number line. We don't know which part, and say that number that it's focusing on is the number which we call n. And so what are the numbers next to it? So this is what we ask the students. So what will you write for the numbers to the right and the numbers to the left? So any guesses about what the students might write? So this Okay. So Joy has said that, okay, M presumably to the left and O to the right, and that's a very good guess. Yes, so you write N, and then the next letter will be O, and so on. Of course, many of you are giving this correct algebraic response. It's hard to remove the spectacles once you've got the algebra spectacles, right? It's but many students don't have those spectacles, and the job of the teacher is to sort of try and wear bifocals so that you see both through the algebra spectacles and through what the students are probably seeing, right? So the students actually wrote N, O, P, Q, and so on, and then we said, okay, what happens after that? And of course, they got stuck when they reached Z, and they didn't know what to do. And more interestingly, of course, if you go to the left, and of course, after Z, you can say ZA or something, or AA or something like that. But if you go back and you reach A, then you're really stuck because you don't know what to write after what comes on the left. So, so this is was an interesting exercise, and it took quite some time for the students to sort of realize and then come to accept that you can write n plus 1, n plus 2, etc. to the right, and n minus 1, n minus 2 to the left.
So Ravi, just one curiosity.
Yeah.
What age students are we talking about here?
So these were the things we tried with class 6 students, I think, yes, class 6. And so this is the beginning of algebra. So they've not yet, maybe they've had some exposure in school, but we are talking about the age when students have not yet encountered algebra, at least in any significant way. They may be just beginning. So, and my focus is on this stage. When students have kind of got quite a bit of experience in arithmetic, they've internalized a lot of arithmetic things. They learn to see things through arithmetic. And now they're encountering something strange and different. Okay, so that's an example of, again, how letters are interpreted. And here you can see that letters are not being interpreted as objects, but they're being interpreted as numbers. But, and here is where it's interesting. You see, the letters of the alphabet are in a sequence. So they might very well be used for numbers as well. And if you look historically, one of the greatest mathematicians was Archimedes, right? The Greek. And if you look at his text, so the Greek notation for numbers actually used the letters of the alphabet. So alpha was 1, beta was 2, and so on. So this was the notation that the Greeks had. Of course, Archimedes did some very clever things with that notation. And was able to write very huge numbers in something called the sand reckoner. He tried to write the number of grains of sand in the universe, or put some limit on that. So, but it's true that any ordered sequence of symbols, which people are familiar with, can stand for numbers. In fact, when children learn numbers, they just learn the words, right? 1, 2, 3, 4, etc. So they're kind of an ordered sequence of tokens, symbolic tokens. And it's only later on that they map this to counting, to quantity, and so on. So it raises some very interesting questions for people in education, that what is really the relation between numbers and these tokens, symbolic tokens, which are ordinal, which are arranged in fixed order. And can any of them stand for numbers? What properties do numbers have over and beyond just these ordinal sequence and so on? So those are very interesting questions to ask. And then you realize that this is exactly precisely what somebody like Peano was trying to do when he tried to axiomatize the ordinal numbers and the number system, and try to define what operations are. And so on. So this is, so behind students' intuitive thinking, sometimes we get insights into what mathematics is all about, or some aspect of mathematics, sometimes also illuminated from the history From cultural, from anthropology, for instance, many cultures have had different kinds of number systems and what representations they use for numbers. All of this is quite fascinating, but we will get into it probably some other time. Okay. Okay, here are some other creative responses that I wanted to talk about. So David is 10 centimeter taller than Con. Now this is a direct quote from that source which is given at the bottom. So what can you write for David's height? Of course, the first one is correct. 10 plus h, that's the right expected one. It's algebraically, someone who's familiar with algebra and so on. So what about the next one? What do you think is happening? So 10h, so you can see that there's no plus sign. And so some students have just joined them together. Now, this is actually, again, some indication of what students intuitively think, that if they what's called sort of conjoin, concatenate or whatever, put one next to the other, then it's like adding up or joining, and it's similar to addition. So they, in fact, intuitively represent addition as this kind of piling up. And we know that in algebra, the convention is very different. It's the opposite. In fact, it is the addition operation that has to be indicated with a sign. And if there's no sign, we take that operation to be multiplication. And of course, there are additional conventions like letters will always follow numbers and so on. But so this, we must remember that actually addition, putting them together is something that suggests itself fairly intuitively. In fact, many people would ask this question: why this is interpreted as multiplication and not as addition? Okay, what about the next one? DH and UH. Can you guess what it stands for? Sort of obvious, and DH probably stands for David's height. And what about UH? Okay, so according to the authors, this is probably stands for unknown height. And here is another interesting one, which is h equals h plus 10. Now, of course, this is, it seems like quite some kind of correct response, because you take one height, which is Con's height, and then you add 10 and you get another height, which is David's height. And so h stands here both for Con's height and for David's height, and maybe something else later on. So this is a kind of flexibility that in using these symbols, which is again quite intuitive. Many students are quite comfortable with using the letter in these different ways to stand for different things at different stages. And that's actually violates the convention, and later on we'll sort of try to understand why the convention is there. So all H's in any expression, or sometimes in a sequence of sentences which are like an argument. So the letters would typically stand for the same number. So throughout that segment or that block. So that convention is being violated here. The other thing, of course, is that the equal to sign, has a pretty strict interpretation in mathematics, that the number on the left, of course, here we're speaking only of numbers, not other kinds of objects. So the number on the left-hand side is the same as the number on the right-hand side. That's what really the equal to sign says. Now, but you know that this kind of conventions are frequently violated by computer programmers. Even those who are well trained in algebra, they do that happily. So that's because we can always compartmentalize, these contexts. Computer programmers will write happily I equals I plus 1, or even that strange symbol I plus, because it's just an sort of instruction to say that increment or increase I by 1. That's perfect. Now, for children, of course, they don't compartmentalize so clearly. So maybe one of the things that's the outcome of learning is to sort of clearly learn what applies in what context. And so sometimes one has to explicitly deal with these things. By explicitly, I don't mean didactically, you have to tell the students, look, this is the rule in algebra and so on, but you have to lead them to recognize this, and there must be space for that in our teaching. Okay, so any guesses about the next one, which is this one shown here, R and 18, what that might be, where that might come from for David's height? Actually, we've just seen that in the previous slide. So if you see the letter H is the 8th letter in the English alphabet, and R is the 18th letter. So, H plus 10 is R. So that's that kind of it. It's a frequent thing in some puzzles and so on, so you will find that as well. And 18 is the same thinking, but expressed in, not in code, but in numbers. Because the last one is again something interesting. 110 centimeters. So some students feel that, okay, no number is specified, but let me take a number, because if I had a number, this is exactly what I do. And so they show that. So let me take Con's height to be 100 centimeter, and so David is 110 centimeters. So this is the sort of rationale behind that response. Okay. So let me pause here. Any comments or any questions or queries? Okay. So let me move on. Now that's a slide. Okay, before I go to that, I just wanted to say that the earlier slide that I showed is from 3 researchers who did a lot of work on algebra education. K. Stacy, Paul Drivers, and Abraham Arkavi. So K. Stacy, in fact, was one of the people who came to Homi Bhabha Centre just as we were starting our research in algebra a long time ago. And she was a very encouraging person. I think many things, of course, we were full of, ideas, crazy ideas about how to go about teaching algebra. And I think her questioning, asking critical comments, pointing us to the literature was very helpful. And we were able to really be efficient and productive. And I just wanted to acknowledge her, which was very important right at the beginning when we were just starting our research. Okay, so this slide is another sort of comment, which is about Piaget. You see, many of these things, these windows into students' thinking, this whole approach in what you might call cognitive psychology comes from Piaget. Prior to that, the techniques or the orientation was not really present to sort of go so deeply into what students are thinking. And that impulse comes from Piaget. And in fact, Piaget's influence has been the greatest on STEM education, science and mathematics education, because they are sort of cognitively dense with concepts. That's to be expected. And if you look historically, it's been even more the case that mathematics education researchers sort of very directly absorbed. In fact, some leading researchers worked with Piaget. One of them was Seymour Papert, another was Vergniaud from France. All did seminal work in mathematics education. So there's also a direct link to Piaget because they're collaborators and sort of the students, mentees of Piaget. And here is a very famous experiment of Piaget, which is called the conservation of number task. I mean, it's a schematic diagram. So on the left, you see a bunch of, say, 2 rows of marbles or any kind of objects which catches students' interest. So they're arranged in such a way that it's very obvious to the student that they're exactly equal. And so the question which is asked to the student is, are they equal? And students say, yes, they are equal. And then what the experimenter does is to go to the arrangement on the right, where the experimenter adjusts those marbles so that they are a little more spaced out in just one row. And then the children are asked the question again, and are they the same? And many children say, no, they're not the same. And ask which is more, and they point to the one which is being stretched out. And this is very surprising for adults. And in fact, it raises suspicion whether Piaget was, doing some kind of a trick, or whether the children were misunderstanding the question and so on. So this has been probed by researchers for, I don't know, 5 decades, half a century, possibly or more. I think it's from the 50s or even earlier, maybe. So 1950s. So there's a lot of research has been done. But what I want to say is that that experimental result is a very robust result. It's been replicated in many different contexts, hundreds of, thousands of times. It's something that you can check yourself. So many of these conservation tasks and the experiments that Piaget did with children, he was a gifted experimenter, was driven by some kind of theory. So even though Piaget's theory may not be accepted wholly today, maybe some parts of it would be, the experimental results are very robust. And somehow his close observation, his theory allowed him to get those insights and to design those very perceptive experiments. And so this is one of them. There are many other conservation tasks and many other things as well, and which I just wanted to mention. So this whole tradition of sort of peering into children's minds can be traced back to Piaget and all the developments subsequently. Okay, now I want to talk a little bit about this specific error. It's called the conjoining error. Boss, I think I'll go on for another 10, 15 minutes, if you don't mind. I think. Okay. So,
perfectly all right.
Yeah. So here is this error, which is pretty familiar to people who've taught algebra, etc. And 5 plus 2x is 7x. The star there indicates that this is erroneous. It's a sort of convention from linguistics. And 5x plus 2y is 7x. So, of course, sometimes, let me see if I have it on this slide. So what explains these errors? Okay, I don't have it. So sometimes, teachers say that, they remember that bananas and apples. So X stands for apples and Y stands for bananas, and you can't really add them. But that's a bit confusing to students because, 5 bananas and 2 apples is 7 apples and bananas. So this is, it's not very clear at all to the students that why they can't be added and why we can't write 7x. So this sometimes researchers refer to as the dangers of fruit salad algebra, as it's called. So and so that's probably not a good explanation for why you can't add them. But I just want to say that first, let's be clear about whether they are really errors. Now, if you say that that's an equation and you say solve for x, clearly that has a solution, and that's x equals 1. And even the other one, if you say, that's an equation, and you solve for x, you can actually solve, and you get sort of open, sort of not one solution, but an infinite set of solutions, and which there's a relation between x and y. And so those are just 2 pairs of solutions. And you can get a lot of solutions. So clearly, they're not incorrect or wrong when you write them as equations. So that's something that we should be clear about. And so they're really errors only when they're interpreted as identities. So what's the difference between an equation and an identity? It's good to, now this actually perspective comes from logic. It comes from people like Tarski and so on. So what's the correct way of viewing algebraic symbolism? And so we say that this sentence here, 5x plus 2, equals 7x. So this is saying that something on the left-hand side is equal to something on the right-hand side. Now this has got the form of a sentence. It's not quite a sentence. It's something like an open sentence. And it becomes a real sentence when you substitute some number for x. And then it becomes either true or it becomes false, because sentences have the property of being either true or false. And so when you say solve for x, what you're saying is what are the values of x for which that sentence is true. So what's the value of that variable? So that's really the language of variables and the logic of the sentences of algebra. And similarly, in the other case, you're asking what are the values for x and y which make that sentence true. Now, of course, when you write these as identities, what you're saying is that this sentence is what you're claiming is that this sentence is true for all values of x. And of course, that has to be defined over a certain universe. And when we say all values of x, we mean all values that it can take from the universe of numbers, from that universe itself. So real numbers, perhaps, or integers. So this is the way we understand it in algebra. So they are sentences, open sentences, and they are either this means you can put any value for x, and in this case for x and y, and then they will be true. Okay, so let's go back to the conjoining error. And I'd have loved to hear your views on why students make that error. And we have seen something just a little while ago, and that also will give you a clue. But let me go ahead because I want to make a couple of comments and then conclude. So explaining the conjoining. Okay, so now reason one is that how students interpret the equal to sign. You know, when arithmetic, they're used to the equal to sign being a sort of command to say do something and write the answer. You know, this is a typical interpretation of the equal to sign. And in algebra, it's very different. It means that the number on the left is equal to the number on the right. And this is something very unfamiliar to students. So there's a lot written on about the meaning of the equal to sign. How it, of course, it can have even other meanings like we saw in computer programming. It can have a different meaning. It can have a different meaning when you define a function or you define some entity. So that is an assignment. So all of these, so the equal to sign can actually have very different meanings. And in arithmetic, it has this very specific meaning of writing the correct answer. In fact, if you look at this example here at the bottom, 8 equals 5 plus 3. You know, once, in fact, this is when I asked students of class 3, when, you know, I wrote a bunch of sentences on the board and asked them to say which is correct, which is wrong. Of course, I had some incorrect things like 5 plus 1 equals 4, which they were very happy to say that's wrong, etc. And this one, they said is also not correct. This is not right. So ask them what's the problem with it. They said it's been reversed. So they said that 5 plus 3 should come on the left-hand side and 8 should be on the right-hand side. And so this kind of gives you a clue that how they perceive this. And in fact, they were very uncomfortable with this last one, which is 8 equals 8. It's just totally flummoxed. They said that there's something very strange going on. They refused to say that that's correct. So they said that won't do. That's wrong. Okay, so that's one explanation for the conjoining error, because students feel that they're compelled to write something as the answer. You know, they have to do something with what's given on the left and then write down the answer. But let's go a little more, little deeper into this. And this is that, okay, so the other thing that students are used to in arithmetic is that answers must have a closed form. They must have some kind of compactness when you write the answer. You know, when you write 5 plus 20, it becomes 25, which is very compact. Now, actually, 25 is not compact. It's just a shorthand for 2 into 10 plus 5. You know, 2 tens and 5. But we're so used to it that we, you know, immediately interpret 25. And we feel that it's one compact object and not kind of code for a certain. Okay. So now what is the correct answer to this? The correct answer to this expression, 5 plus 2x, if somebody, you know, who knows algebra better, will simply write 5 plus 2x. That's the same, right? Now, this is, to students' mind, this is a kind of cheating. You know, kind of cheating. Because when students have, you know, are writing an exam and they get this question paper and they don't know anything about what the question is asking. So they have this trick of writing the question itself as the answer. You know, this is an old trick. Many of us might have used it as kids. So you write the question itself as the answer. Oh, and this is exactly what you're doing here. You know, you're writing the question itself as the answer. How is that possible? That's simply not acceptable. No, it can't be. So this is something that, so the question itself, the question is telling you, you must do something, you must carry out some operation. And you can't write that as the answer. So because answer has to be different from the question. In fact, this is what is called the algebraic principle. And it's good to pause here. So it's some researchers have called it the process product duality. That is, in algebraic symbolism, something stands for a process. So 5 plus 2x stands for a process, which is that you take a number x multiplied by 2 and then add it to 5. And it also stands for the result of that process, which is the answer that you get after completing that process. So it is both the process as well as the product. So this is the process product duality. In other words, it stands both for the question as well as for the answer. And this is an important kind of insight. And like the insight about the meaning of the equal to sign, this insight can also be very powerful in designing the right sort of learning experiences in algebra. And that really is the test for whether that insight is valid or not. Okay, so there's a reference there, and I've talked a little more about that, but essentially this is the idea. And so the process product duality is what I call the algebraic principle. And the principle is that use the representation for the operation also for the result of the operation. And that's important in algebra because now we can not only symbolize the result, but we can even operate on it. When you say add 2 to x and the answer is x plus 2, that is it. That's the answer. Now you can take that x plus 2, you can do things with it. You can add it to something else. You can multiply it by 3. You can square it. You can, and do all kinds of operations. So operating with expressions becomes possible when you designate the symbol for the operation itself as the result is the operator. So it stands for that now. So that's the insight of algebra, the algebraic principle. And if you think about it, it's not very different. I mean, it's not that it applies only in algebra. In fact, that's the example here, which is the example from fractions. So, in fractions, exactly the same principle is used. Now, 8 divided by 2 is nothing but 8 by 2. 8 by 2. It may not be obvious in the case of 8 divided by 2 because clearly it has a solution in whole numbers. You write 4. And so that's the preferred way of writing. But if you take 27 divided by 31, nobody is going to there's no whole number. So you just write 27 by 30. In fact, that's again the algebraic principle. You're just designating something that's an operation to stand in for the result of that operation. And now you kind of appreciate why students have difficulty with fractions as well. Because when you say add 2 fractions, 2 by 3 plus 5 by 7, you're not adding just numbers per se, but you're adding things which are quotients, which are the product of division operation. And you kind of used an algebraic principle to symbolize that. So what you're adding is the result of dividing 2 by 5 to the result of dividing 5 by 7. And that's quite complicated. So it gives you kind of insight, not necessarily a clear path on how to teach fractions, but why fractions are difficult. And to some extent, this is even true of negative numbers. Fractions are formally defined as the equivalence class, right? 8 by 2 is the same as 12 by 3 or 16 by 4 and so on. And these are all the same fraction. So fractions or rational numbers are equivalent classes. The whole set is just one rational number really. And similarly, one can also think of integers as equivalence classes, and people have defined this like this. So minus 2 would be the result of the operation 0 minus 2, or 2 minus 4, or 3 minus 5, and it's equivalence class for these operations. So you can think of integers as also kind of applying the algebraic principle. It gives some insight, and maybe some occasion we can talk more about fractions because our work has been mainly in this algebra, fractions, and integers, and we can also discuss that. Okay, so the algebraic principle is also applied to these things, and that's really so why do we need to operate with expressions in algebra? And this is because This is a typical feature of the algebraic approach to solving problems. And the arithmetic and algebraic approaches are very different. And this is something that I wanted to talk about. But I realized that we're kind of running out of time. And this will take me another, maybe 7, 8 minutes, 6, 7 minutes. And I leave it to Bas whether I should pause here for questions.
Ravi, I think we can go ahead. This is a very interesting point we have come to.
Okay, all right.
So I think another 7, 8 minutes is fine.
Fine. Okay. So let me try to illustrate this through example. And this it's one of my favorite examples. So it's something very simple. And I hope you enjoy it. So here's the problem for you. Now, don't type the answer in the chat box. This is, it's only valid for 30 seconds because we're a little short of time. Don't speak out the answer. Try not to use algebra. In fact, the third rule is the most important rule. Don't use algebra. And then let's see how you solve the problem. And this is, okay, that's the problem. A farmer had hens and goats. He counted 50 heads altogether and 144 legs. So how many hens and how many goats did he have? So try and do this without algebra. So you've got 30 seconds. And I think it's good to think about how you're doing, and we can discuss that. Okay, so your time's up. So what is the solution? I'm sure many of you got some answers. Some of you might have found it difficult to 61. No, there are only 50 heads altogether. So how many hens and how many goats? I hope I have not confused people. I'm sorry if I have. Any answers?
22 and 28, I think.
22 and 28. So is that right? Okay, let's see. Okay, so since Bas replied, so how did you solve the problem? Bas, was it guess and check?
No, so I did the following. There are 50 heads. So 100 legs are given, irrespective whether they are goats or...
Then hold on. Okay, we'll come to this. So that's very interesting. Huh? So some of you might have used algebra, and I wouldn't hold it against you. I think it's quite obvious. So just say X and Y, and then found a way. Some of you like Bas, and I'm sure there are others who found a way of solving it with just arithmetic. Okay. Now, that's the algebraic approach. So x plus y is 50 and 2x plus 4y is 144. And then you solve the simultaneous equations to get x and y. Now, suppose you just use arithmetic. And here are a couple of different ways of reasoning. Now, that's exactly what I think Bas started with, that 50 hens, let us say, that's 100 legs. If you assume that all of them are hens. So the total number of legs is 100, you have 44 legs less. So you need 44 extra. And suppose you exchange a hen for a goat, you will get 2 extra legs. And because you give 2 legs and get back 4. So, right, that's what it says. And so if you exchange 22 hens for 22 goats, you get 44 extra. So that's one way of reasoning. Okay, that's a kind of compensatory way of reasoning. But here is something that, some student actually used. And this was reported to me by a teacher, and it's quite fascinating. So let's see how the student thought. Hens and goats altogether are 50, right? So because there are that many hens. So what the student said is, let's count the hen's 2 legs and only the 2 front legs of the goat. Right? So this gives us 100 legs. So the remaining legs must be hind legs or back legs. And so there are 44 of them. And so there are 22 boards, and the rest of the 50 are here. So this is so it's very clever. So the point I think I want to suggest is that arithmetic can of course be used to solve problems, but it requires a lot of ingenuity. It requires some ways of thinking. Of course, this problem is very simple. You can just guess and check. But there are many problems if you go historically and look at how people solve problems without the use of arithmetic with some kind of compensating principle. Sometimes they're very clever. There's very clever uses of arithmetic reasoning that leads to solutions of problems. In contrast, there is no, algebraic reasoning doesn't require any ingenuity. It's kind of mechanical. You just put down something and you just follow the steps. And that's what you really get. So it's routine in some sense. And if you see, it didn't involve any concrete reasoning, except in the first step. You say x, the number of ends, y, the number of votes, you set up the equation, and then you just manipulate equations and variables and numbers without bothering about what they really mean. And so an interpretation comes back only in the last step. So here is a sort of closer view, and with this I'll conclude, which is to look a little more closely at the algebraic approach. You see, we set up the equations for heads and legs. That's equation 1 and 2. And then from 1 multiplying by 2, we get x plus. Okay. Now, what does multiplying by 2 mean? So there's a number on the left-hand side, there's a number on the right-hand side. So 2 times this number is equal to 2 times the number on the right. And so the number, you know how to multiply this by 2, which is 100. You don't quite know, and students may not quite know how to multiply this number, so-called number by 2. And of course, you need to represent that. So that's why we write the question itself as the answer, in some sense, and then so this is what we call operating on expressions. And that's why it's necessary. And then we subtract equation 3 from equation 2. And so I've written that subtraction here. And so you need some algebraic facility in use. So this is kind of gives you a idea of why we need those unclosed expressions, why we need the algebraic principle, and we need to learn these rules. Because the typical algebraic way of solving equations, and this is what is also true historically, is to simply write down those unknowns, operate with them. The result of that is again written down in the form of an expression and so on. So that produces a very mechanical approach, and doesn't need any ingenuity to solve. Okay, and that slide sort of summarizes the differences between algebra and arithmetic. That in the algebraic solution, the unknown is fixed in the beginning. It remains, so x is the unknown, y is the unknown, and it continues till the end when those values are found. In the arithmetic solution, actually, unknowns change at every step. First, you find, for example, the total number of legs if you have only heads. Then you find out how many legs are less, that's 44. And then you arrive at some other kind of reasoning. And then you do one unknown at a time till you finally arrive at what is to be found. In algebraic approach, you represent the entire sequence of operations. In fact, that tells you why in algebra you have both the plus sign, the multiplication sign, everything together, and you need some convention for the order of operations, because the entire sequence of operations has to be represented. In arithmetic, you just do one binary operation at a time, and that's what you're supposed to do. Mathematics, binary operations have to be strictly sequenced. You can't do multiple operations at the same time. There has to be an order. So you set up an equation. The equal to sign has a certain meaning, equal value on both sides. We saw that. But here, equal to sign means do the calculation, write the answer. There's no interpretation of quantities in the intermediate step. In fact, you will get things like 44 even in the algebraic approach, if you noticed carefully. But you don't interpret it. Nobody interprets 44. But in the arithmetic approach, you have a clear interpretation for what that 44 means. And the intermediate quantities are meaningful. Operations are done on symbols and operations are done on numbers. Okay, so that sort of is the summary of the differences. I think that those are the main points. And that is the slide at which I stop. So this, just to briefly sort of preview, this led to an approach to teaching algebra, which we tried, where we try to begin with looking at expressions, trying to understand them, and develop this approach. So this approach we've written about. Of course, it's something that needs to be tried different people to validate. And I must also conclude by saying that this is only a kind of fraction of the research that's done in algebra, I mean, a small part. And there's much more to algebra and algebra education. It's a pretty vast area of research, which has been active for several decades, still continuing in some way, although a lot of insight has been made. So let me stop and take some questions.
So, thank you, Ravi. There's already a question here in the chat box from Ashok Rao. More of a comment than a question. He says that one generic issue appears to be that we start with arithmetic and numbers first naturally by counting fingers, but later introduce symbols. We will have different issues if algebra were taught first and later arithmetic.
Right. Now, that's a very interesting point of view. And let me just clarify. So there is something, now algebra, of course, we associate with X and Y. And I suppose it would not be reasonable to start just teaching X and Y unless they have some meaning. Some meaning is given to students. So you would either start with numbers, and there's another approach which is called
No, one,
yeah, okay. Now I think it can. All right.
it sounds an exception maybe, but if you look at Norbert Wiener, he had serious problems with eye. So his father switched him from arithmetic to algebra very early in life.
Okay.
So for the rest of his life, he was a wizard in manipulating symbols, but he was quite bad with manipulating numbers. I mean, his whole career was so abstract, and as long as they were symbols, he would get everything right. But as long as they were numbers, he was struggling hard, most of the time going wrong.
Yeah, sure. So I think then your point is that one need not wait for numerical fluency to introduce algebra. So some, introduction to what numbers are, and then you can move on to algebra. And that's an approach that's been tried. So what people say is that algebraic thinking is more important than just the use of symbols in algebra, and that algebraic thinking can be introduced quite early. And that becomes also a natural way to introduce symbols. For instance, let's say what happens when you increase a number by 10? Or what are the different ways in which you can add, say, 48 plus 49? How do you show these different ways of adding? And so the many such insights, which are insights about the properties of numbers or the relations of numbers, and they can be captured with the right kind of notation. So children get out of this habit that when you see symbols, you just have to do an operation and write the answer. It's also, symbols can be used to show relations between quantities, between numbers, and one can even generalize those kinds of relations. So that's what's called early algebra, and that's a very active area of research. And yes, so bringing in algebra or algebraic thinking early is something that's been found to be productive. Again, there are different approaches, and one other comment about, say, somebody like Veena. I mean, there will be students who learn in very different ways. That's also something that we need to keep in mind. And so a teacher who's flexible and who has some kind of a perception of what's important and what these differences are can suitably modify her way of teaching different students, and encourage students who are more comfortable with something different from the standard approach. I think that's also one can keep in mind. I mean, there will always be people like Wiener and other kinds of students who think very differently from most students think differently from each other. And I think that's an important pedagogical insight.
So Ravi, I had a question, or rather, more a question actually, not so much for comment. So this expression like 7x plus or whatever, 4x plus 3y is equal to 7xy, which you had, or I think it was 5 and 2, bananas and apples. So is this difficulty perhaps related to the way people learn to express themselves without numbers when they are using just objects, and when they realize that when you combine in this instance, you combine 5 apples and 2 bananas, they are 7th fruit, right? So the xy is a placeholder for fruits in their
That's right.
thinking.
And in fact, it tells you what kinds of fruits also. They are apples and bananas.
Perhaps, yes. So if there's a third fruit, they'll probably write XYZ.
Yeah, right.
And this probably extends to other things also. Like, if you are saying men plus women and then just say people. So when you're talking of collections, or when you're talking of collective nouns, for instance, you can make this interpretation, that you can add 2 different kinds of things and come up with something that is more and part of a larger collection. So the larger collection needs a placeholder, and the placeholder is there in their language.
So yeah, right.
In their expression in terms of words, but perhaps not in terms of these symbols. So they try to somehow fit a symbol to what they think in terms of words.
Absolutely. This is so how do we use symbols? Symbols, I think human beings have a natural propensity to invent symbols, to infuse them with meaning, and to use them, in very flexible ways. So algebra, in fact, is the regimentation of that kind of intuition. It makes it very strict. Of course, later on, I think in algebra, some of the fun comes also from relaxing these rules and seeing what happens. That's also part of the fun of algebra. But when students are sort of getting introduced to using letters to stand for numbers and learning the power of that, so that's that kind of flexibility has to be regimented. That what they have to see is that each of these symbols stands for numbers of one kind or another. And at the same time, it gives some insight into the number. I mean, just as we saw that X and Y sort of may give the insight that there are 2 kinds of fruits. Now, that's from outside the world of algebra. But in fact, that was the starting point of our teaching, that an expression not only stands for a number, but it tells you something about how that number is made up of other numbers. So this is what I call this operational composition. So an expression gives an insight into the operational composition of a number. And that's a very important sort of insight. So students have to get into the habit of reading expressions and reading through them to see the numbers as well as what those numbers might represent in the real world. So a large part of teaching algebra and to sort of using these new spectacles is to learn to read. Learn to read those symbols. And that they can get a lot of help from teachers.
Ravi, there's one more question, perhaps the last question for today. Is there a relationship between comfort with algebra and comfort with randomness in general or in the surroundings?
Okay. Now, this is an interesting question. I'm not very sure what Chavi has in mind, but let me guess and respond, and then Chavi can correct me. So, I think if I understand Chavi, so she's asking, why are some students more comfortable with algebra? That's certainly true than other students. And where does this comfort come from? Now, I mean, I tend to believe that this comfort is there more among students. Now, this is not, can't be generalized too much, and it's a bit of a hunch. It's not some research-based thing, but more from my own teaching or looking introspection. So students are comfortable when they are, those students are comfortable who are accepting of rules, accepting of some kind of arbitrary rules coming from authority. I mean, I'm making a slightly provocative statement. You know, those students who do well are students who kind of accept, okay, this is the rule, then that's it. They'll accept it and I'll go by it. And they have a lot of fun in applying that rule. Now, of course, the students who have discomfort with that are the people who wonder, why is this rule so? Why can't the rule be different? Or they have trouble remembering those rules and they just can't appreciate why they have to follow these rules or listen to them and obey them.
But Ravi, do these, sorry to interrupt, but do these students like to know where the rules came from or why they are likely to be correct?
I'm sure they do. I'm sure they do. If that kind of a conversation is triggered. Now, of course, I mean, they will not express themselves unless the classroom environment is such that they're comfortable in raising questions. And once you open up the classroom and make the environment comfortable, questions will come and those students will ask questions. So the comfort, I would say, is the comfort with kind of accepting some kind of rules and enjoying playing with those rules and seeing where they lead. That might be the case. So I don't know if I misunderstood what Chavi is asking, but she can elaborate a bit if she wants to. Okay, yeah, thanks. Okay. Right. Yeah, she said that that answers the question.
Okay.
So I'll just stop sharing.
Right. So Ravi, I think we can stop now. 7:15. It was nice. It was a nice talk. Very nice insights into how students face or what kind of difficulties students face, and maybe this gives us some hints as to what we should be exploring in order to make some of these things easier. And I suppose maths is always a difficult or seen as a very difficult thing by a large number of students, no matter what stage they are at. Certainly in school and even later, I guess. So I hope there's more work in this domain and we get to see better ways of teaching maths and so on. And I also hope that you will come and meet us next semester in person when we have another set of talks later sometime.
Yeah, I hope so.
Right. Yeah. Okay. So thanks a lot, and we can now break. Bye, Ravi. Thanks a lot.